please, you can start.
Yeah, I was muted. Oh, yeah, thanks. Thank you for the great opening, no? And I want to talk about a new binary evolution channel during the AGB phase. And this work has been collaborated with Natalia Ivanova and Jonathan Carroll-Nellenback. And my former collaborators include Adam Frank, Eric Blackburn, and Jason Nordhaus. And this work will also, this presentation will also include my previous work. So let's begin. To motivate you, I will first show some evolved binaries observation. And this is the AL pop. And the two bright lobes are the scattered light from its pole direction. And there is a dark band in the middle. And this dark band is likely the dusty torus or dusty disk, circumbinary disk. This object is not resolved as a binary because it's not resolved, but we infer that from the dark band, we infer that there is a binary in the center. And the second example is the L2 pulp. It's also taken by Zimpo, and the two bright lobes are also scattered light from the pole direction. And we have seen we resolve the binary and we can confirm that there is a binary in the center. And the dark band is also a circumbinary disk, dusty disk. Let's look at another morphology. It's the spiral morphology. And this picture is taken by Alma. And this is the middle plane or velocity equals 0 of the channel map. And we can clearly see that there is a spiral structure inside the biggest ring. And also we can see that the alpacacy has a similar morphology. So they are all evolved binaries, probably. But they have very different morphologies. And while some of them have circumbinary disk, but some of them have spiral outflow. And my thinking is that the reason behind this is the mass transfer modes. And for your information, I will introduce the Windrush flow first, firstly introduced by Mohammed and Podolsky. And this mechanism, because the AGB star has a large dust formation zone at large radii, when this dust formation zone overlaps with the inner Roche-Lobe radius, the secondary can impose great gravitational pull to the material in the dust formation zone. Because the material, the gas in the dust formation zone is usually subsonic or has very low Mach number, the gas will be influenced by the secondary strongly. On the contrary, if we increase the binary separation and the dust formation zone is well inside the inner Roche-Lobe and then the wind from the AGB star becomes supersonic, with Mach number probably above 4 or 5, but it's supersonic. Then the two stars, the AGB star and the secondary, become causally disconnected in hydrodynamics. So the secondary can no longer impose great gravitational pull to the wind. And in this case, a Bondi-Hoyle-Littleton accretion ensues. And for Bondi-Hoyle accretion, for BHL accretion, typically there is a accretion column. This is the material that the maximum amount of material that the accretor could accrete. In reality, in binary, the binary have angular momentum, and not all the material can be accreted. So this accretion rate in the accretion column is the upper limit of this accretion mechanism. So for Windrush lobe, on the other hand, we usually normally have higher mass transfer rate, and they may yield chemically, they may be the progenitor of some chemically peculiar stars. For example, the baryon star, and they may have long-term orbital impact. And to distinguish and to show the transition from the Windrush lobe flow to Bondi-Hoyle-Littleton accretion, we carry out simulations with astrobel, 3D radiation-hydrodynamic simulations. And we first construct a phenomenological AGB pulsating AGB star, and the left figure shows the density. The right figure shows the optical depth from the surface of the AGB star. And yeah, so as the simulation goes, the secondary accrete material from the AGB wind and form an accretion disk. And the accretion disk casts a strong shadow behind it. And we can also see that the optical depth of this region is usually around 0.3 or above 0.3. And this is very, it actually is in the limit that the gas cannot escape from the binary. And a second binary, the material is bounded to the binary, and the second binary disk just formed. To carry out the radiation transfer, we use ray tracing, and the center of the mesh of the radiation mesh is located at the center of the AGB star, because this is the radiation where the radiation force come from, and we use adaptive mesh. And to address that, we are not carrying out post-processing. The radiation force and the hydrodynamics are coupled. So if we enlarge the binary separation, we reach the Bondi-Hoyle-Littleton accretion limit. And in this case, we can see that the AGB, the secondary also accrete mass from the gas from the AGB wind and form an accretion disk. Similarly, the accretion disk also casts a strong shadow behind it. However, in this case, the optical depth is much smaller, and the radiation pressure on the material is very greater than the first case, and the gas just keep it flowing out and form a spiral structure. So what causes so this is the gallery of these two distinct simulations. And we, on the third and fourth column is the temperature and the side view. In the side view, we can see that the accretion disk is actually thin. They are thin disks, thin accretion disk. And what causes this very strong difference, as I said, is the mass transfer mode. But there is a deeper reason. And this figure shows the difference of the wide and closed binary.
3 minutes.
For closed binary, they have typically deeper potential well, gravitational potential well, and they will lead to more focused gas into the middle plane, and the material just stay in the middle plane and block more radiation from the AGB star. And the gas and dust will gain less radiation pressure, or photon carry the momentum from the AGB star. And they cannot radially move radially out, and the gas and dust just trap in the middle plane and form a second binary disk. And this process involves the focusing of the wind from in the polar direction or in the r theta direction, and this gradual increase in the optical depth has interplay with the R5 direction. So this problem is intrinsically 3D and it is very computationally demanding. The impact is not only morphological, it also has dynamical influence. So the mass transfer rate of the when circumbinary disk form is much higher than the boundary Hoyle-Littleton accretion efficiency. We can see in the red color, the mass measured transfer rate is as high, could be high as 8 times of the upper limit of boundary Hoyle accretion rate. And the mass transfer and the angular momentum together, they can have an impact on the period change rate. And the binary can get closer if they are close, starting close. The x-axis is the binary separation. To understand this picture, the blue stars are the period change rate for boundary Hoyle accretion, and the green squares if are the rate that if they are they have conservative mass transfer. But in reality, in our calculation, we find that the large separation follows the boundary Hoyle, but in the closed binary, they are more like conservative mass transfer evolution. So in summary, we have discovered a very important intermediate mass transfer mechanism. This mechanism is happening at in AGB binaries, and they have accretion disk and circumbinary disk, and they may become the progenitor of some of the planetary nebulae. And I will put my summary here and take any questions. Thank you.
Thank you very much. So now it's time to ask questions or to give comments. We have 3 minutes for that. Please.
Can I ask something?
Yes, Dr. yes, please.
Very nice talk, amazing simulations. Can you tell me what is the mass and the size of the circumbinary disk that you're getting? What is the range? Because that is something which you can observationally test.
Oh, yeah. So in my paper, I have gathered the information of roughly 20% in this case, in the closest case, 20% of mass stay in the middle plane.
Okay, but what is can you give me a number in like solar masses?
So if the mass loss is 1 solar mass, then 0.2 solar mass should stay in the middle plane.
No, but you have a mass loss rate. You don't have a total amount of mass lost, right? I mean, I'm a little confused. I mean, if observationally we observe the mass loss rate from the primary, we don't really know what's the total amount of mass which is lost because we don't know the period over which that mass.
My point is, if you have 1 solar mass rate, you have probably 0.2 solar mass piling up rate in the middle plane.
But 1 solar mass ejected over what period of time?
Whatever time, you can just divide it by a time and then divide by the mass piling rate by another time. It's the same. For example, here I have, it's in the paper. I will encourage you to read the paper. The mass transfer rate, mass loss rate is different because the tidal interaction.
Yeah, all I'm saying is we can continue on the Slack channel is that as an observer, we observe the mass loss rate. We cannot easily infer the total amount of mass lost. So it's a little bit difficult.
Sure.
Okay, but sorry.
Yeah.
Okay. Guillermo?
Yes, what is the mass ratio in your simulations?
Oh yeah, that's a good question. So in this dark band, gray band, the mass ratio is 0.1, but all other cases are 0.5.
this is a problem that I see here because, for example, in the Frank-Zhu analytical equations, you see that you can form the circumbinary disk above 0.78, and that's without radiation pressure on dust. So radiation pressure inhibits the formation of the circumbinary disk when you include it. So I don't understand why Frank-Zhu got 0.78 and you go down to 0.5, which is even worse. I don't understand that.
Well, which number are you referring to? Which number?
You tell me that your ratio is 0.5.
Oh yeah, because I have radiation pressure. Yeah, I remember. Yeah, Frank-Zhu, they when you have a circumbinary disk, your gas can get around and interact with the accretor, the accretion disk, for many times, and you don't get a single interaction. So the angular momentum transfer and also the mass transfer is enhanced.
No, my point
is his picture is very ideal. I mean, this is a radiation hydro.
Yeah, but without the radiation pressure, you form circumbinary disk above 0.78, the ratio of the masses.
So that's the classic theory. So the new numerical simulation say that this is the new numerical simulation.
Okay, Tomek, we'll move forward. Tomek, please.
Hi there. So my question is whether those circumbinary disks are stable, or what is the time scale on which they are stable, including radiation of the AGB star?
Yeah, that's a great question. So because the AGB star, the boundary is both inward and outward. That means the material can get in and out by hydro pressure. So in my case, the angular momentum conservation is not perfect. So you don't get like in the planet formation, the planetary disk, a very stable Keplerian disk. But in this case, the radiation pressure is significant and everything is dynamic in this range. So it's not a question of stable. However, I think there is a defect here because I should carry out the energy coupling of radiation hydro too, but I only carry out the momentum. If you calculate the radiation hydro for energy balance, you will get a smoother circumbinary disk, and the part of the circumbinary disk will be supported by pressure, and part of the disk will be supported by Keplerian motion. But they are never, I don't think with this mass ratio, you will get a very stable disk in 20 AU or so. Yeah, they are too massive. The central stars, they are too massive.
But if you switch off mass loss, then you also lose the disk, right?
Yeah, after several orbits, the disk will disappear because they expand, but some of them fall back.
All right, thank you.
The outer part expand, but the inner part fall back.
Mm-hmm.
Okay, so please unshare your screen, and Vincent, please share your talk, and we'll go to the next talk.